Welcome to Graphs and Functions, Example 9. Example 8, I introduced the idea of a point of inflection, what it was, the idea of concavity, and how we could identify whether a function had a point of inflection. So we're going to have a look at a different function, and this time in example 9, find the coordinates of the point of inflection of this function. F of x equals 3x cubed minus 18x squared minus 7x. Okay, so the first thing is to identify where a possible point of inflection could be, and that's when the second derivative is equal to 0. So let's go ahead and say if that's the original function, then the derivative of that function is going to be 9x squared minus 36x minus 7. And we can continue to the second derivative and say that that's 18x minus 36. Okay, so we can say that we've done a second derivative. We want to analyze a possible point of inflection, so let's write that down. Possible point of inflection, and you can use a C or an X in flexion when the second derivative is equal to 0. It's always good to state that particular fact, just as you would state stationary point exists when f dash x or f prime x equals 0. Okay, so you're stating a fact that we're looking for. In other words, we can put those two together. Our second derivative is 18x minus 36, and we want to study it when that value is 0, and we can rearrange that and solve that x is equal to 2. There may be a point of inflection, but there may not. So that's why I've used the word possible point of inflection. What we need to do is to check the concavity. And that's us drawing our nature table, I suppose, is the most familiar expression for it. You're probably familiar with that. So let's draw our nature table. 4 columns, effectively 3 columns that we're going to write in, and then just our labels at the side. So on the left hand side we've got the x values go in the top, we've got our second derivative we're going to think about, and if you want to write in what that is, it's 18x minus 36. And we also want to think about then the nature of the concavity. Concave, up or down, we're going to write in there. So what are the 3 places we're going to fill in our column? Well, x is 2 at the possible point of inflection, and we want to study a value of x just below 2 and one just above 2. It's fine at the moment just to go with whole numbers. It would kind of make sense just to use positive 1 and positive 3. There's no other points of inflection kind of before that, so I think we're good to use 1 and 3. We know that when the second derivative at x equals 2 is 0, because we've just worked that out. But what about the other ones? So when x is just 1, if we use 18x minus 36, 18 minus 36 is negative 18, so our second derivative value is negative, which is concave down. Okay, it means that the second derivative, it means the rate of change of the gradient is falling. It's going from positive values through 0 to a negative value concave down. And say if x is 3 and we substitute that into 18x minus 36, we get a positive value, and therefore it's concave up. Okay, so we do have across the 0 point, we do have a change in concavity. So we do have a point of inflection. So we can write down change in concavity. So point of inflection when x equals 2. Now we're asked in the beginning for the coordinates of the point of intersection, so I would go ahead and work out the y-coordinate. Y-coordinate at x equals 2, isn't it? So we're back to our original function. F of x equals 3x cubed minus 18x squared minus 7x, and I'm going to substitute 2 in for x. And work that all out, and we get negative 62. Okay. I wouldn't, well, let's do what I would expect you to do, which would be to actually reason that out. So we've got 2 to the power 3 is 8 times 3 is 24. 2 squared is 4, multiplied by 18 is negative 72, and then we've got minus 14. And if you do all that, you end up with negative, see, you don't end up with that. Yeah, you do. Don't know what I was thinking. Negative 62. So our y-coordinate is negative 62, so we can say in the end that our point of inflection is at the point 2, negative 62. And I just realised again, of course, that that's a lot of rubbish. The point of inflection is when x equals 2. Okay, I was so busy thinking about example 8 when everything was 0. So it's important that the point of inflection when x equals 2, y-coordinate when x equals 2, and our point of inflection is 2, negative 62. Okay, so I hope that's helpful studying where we might find a point of inflection. You might, in a function, of course, if your second derivative was a quadratic expression, it's possible that a particular function has 2 possible points of inflection. In that case, you would just take each case separately and identify if one or both or none of them are points of inflection. So we could have to do this. We might have to repeat this more than once for a particular function. Okay.